Good day guys, welcome back to Wiki Science YouTube channel. In this video, I'll put you guys through on how to determine the refractive index of a medium, as well as knowing the resultant effect of having varying refractive indices called refraction. Also in this video, we'll be dealing with some reference questions, so sit back and watch this video in detail. If you are new to this channel, ensure you subscribe and share this video with your friends. And if you've been with us before, I appreciate you so much for your support. Let's get started. Refractive index simply means the degree at which wave will move in varying medium. So when wave move from one medium to another, they possess a refractive index. Now we'll consider several media. In this case now, we can consider air, we can consider glass, and we'll consider water. Simply now taking this particular glass prism, this is the region of air and this is the region of the glass. So now when we have light wave moving from this air to the region of the glass block, the direction simply change. The change in direction is what we refer as refraction. Now to this particular plane surface, this boundary where this refraction took place, we can have a perpendicular line drawn. The perpendicular line drawn there is called the normal. So we have a normal drawn like this. The angle to which the incident ray makes with the normal is called angle of incidence. And angle to which the refracted ray makes with the normal is called angle of refraction. To determine the refractive index of this light, we say that the refractive index of light moving from air to glass can be taken as the refractive index of this glass, which is the second medium, over the refractive index of air, which is the first medium. However, taking Snell's law, using Snell's law, we can determine that the refractive index is equal to the sine of angle of incidence over sine of angle of refraction. But what I want you to know here is that we can also have reversibility of light to determine the refractive index, meaning that we can determine the refractive index of light moving from glass to air. How do we determine this? If I'm to determine the refractive index of light moving from glass to air, we simply take it as the refractive index of the second medium. So the second medium here simply means air, and the first medium here is glass. When you take the product of these two, we have the refractive index to be taken as the product of these two refractive indices. We take it to be air to glass times glass to air is equal to what you have here, which is glass over refractive index of air times the refractive index of air over refractive index of glass. When you cancel this out, we have the product here to be 1, meaning that the refractive index of first medium to the second medium and the refractive index of second medium to the first medium is equal to 1. That is air to glass and glass to air. So here we have it now that the refractive index of air to glass is equal to the reciprocal of the refractive index from glass to air. So when I tell you now that the refractive index of wave from glass to air is about 1.5, then it means that the refractive index from glass to air will be 1 over 1.5. So this is what we have for glass to air reversibility. Because refractive index of light varies alongside with the velocity, meaning that the speed at which the light moves in air is not the same as the speed to which it moves in a glass. We can as well determine the refractive index to be of air to glass to be the speed of light in air over the speed of light in glass. Because we all know that speed of a wave is generally taken as a product of frequency and wavelength. However, the frequency of light in air and the frequency of light in glass is the same. So when we take the refractive index of air to glass to be the product of frequency and wavelength in air, over a product of frequency and wavelength in glass. The frequency is the same, so this cancel out. Then we can generally take it now that the refractive index of light moving from air to glass can as well be taken to be the wavelength in air over the wavelength in glass. I also want you guys to know here that the corresponding effect of this change in wavelength is what also results into what referred to as dispersion. And what is dispersion? This is the separation of white light into its component colors. So when white light passes through a triangular prism, it definitely separates into different color components. These color components are what we refer to as the Roy wave, where you have the red, orange, yellow, green, blue, indigo, and you as well have violet. In this case now we are considering the glass prism, this glass prism. So the refractive index is inversely proportional to the glass prism, meaning now that the red will be having the highest wavelength and the least refractive index, and this violet will be having the least wavelength and the highest refracting index. So now we'll quickly take reference question on this aspect before we proceed further. Taking this question for instance, a ray of light makes 30 degrees with a plane surface. If the angle of refraction is 45 degrees, calculate the refractive index. Now here we have that, let's assume this is our glass block and we have ray of light making angle of 30 degrees with the plane surface. So this is where we have the plane surface and we have the refractive index to be about 45 degrees. The refractive index to be about 45 degrees. What I want you to know that is that this 30 degrees is not the angle of incidence. I've told you earlier that the angle of incidence is the angle to the normal. So this is angle of incidence and it's said to be 60 degrees because this is 90 degrees all through. 90 minus 30 will give us 60 degrees and this is the angle of refraction. So we have from Snell's laws that the refractive index is equal to sine of angle of incidence over sine of angle of refraction. So here we have that our refractive index is equal to sine 60 over sine 45. We'll be considering the short form in this aspect. So here we have your refractive index to be sine 60 in short is root 3 over 2. Root 3 over 2. While sine 45 in short form is, that is 1 over root 2. We have now that our refractive index is root 3 over 2 times root 2 over 1. So root 2 over 1 and therefore we have root 6 over 2. So this is our refractive index. The refractive index here is root 6 over 2. We'll take another question now. Here we have another question taken from UTME 2015 question 16. And the question states that if the speed of light in water is 2.26 times 10 raised to the power 8 meters per second and the velocity of light in air is 3 times 10 to the power 8 meters per second, we are to determine the refractive index of water. So in order to do this, considering the formula which I've given you, that the refractive index here is taken to be speed of light in air over the speed of light in water. Because we are not using glass now, we are using water, so we are considering water. Now the refractive index is 3 times 10 raised to the power 8 over 2.26 times 10 raised to the power 8. So this will cancel this, then we definitely have it that our n is equal to 3 over 2.26 and that will give us 1.33. So 1.33 is the answer. Now we'll move to another section of refractive index in this video and we'll be bringing in reference question as usual. Relax and remain attentive. Now for instance, if I should take a glass block as usual and placed beneath a pin here. When you look from the surface, there is a particular height which you see this pin to have existed in this glass. It might occur to be somewhere around here. In this case now, we call this particular depth, we call it the apparent depth. We call it the apparent depth. But we all know that the thickness from here to this point is the real depth. Let's call it R. This is the real depth. Now in this case now, I want you guys to know that the difference between the real depth and the apparent depth here, which is this remaining portion that which has been excluded, is referred to as the apparent displacement. This region is called the region of apparent displacement. So in one word, if you are asked to determine the apparent displacement, your apparent displacement is said to be the difference between the real depth and the apparent depth. That is what we refer to as the apparent displacement. But in this case now, determining the refractive index, we have that the refractive index is taken to be the real depth over the apparent depth. The real depth over the apparent depth. However, in some cases, we always consider this type of glass block of the same type, like of the same nature, but with different thickness. When the thickness is said to be different, it means that there is a change in the thickness. So in this case now, when you come across question in such form, just take note that here your refractive index can as well be the change in real depth over the change in apparent depth. So if I should give you that the refractive index of a glass block is 1.50, and we have the real depth to be the change in real depth to be 80 centimeter to 100 centimeter. Now in this case now, I can ask you to determine the change in apparent depth. Since the real depth is this, the change in real depth is said to be 100 minus 80, and that is 20 centimeter. So now if I were to get the change in apparent depth, the change in apparent depth will be refractive index equals change in the real depth over change in apparent depth, and the refractive index is said to be 1.5 is equal to change in real depth is said to be 20, change in apparent depth is what we're looking for, and from here our change in apparent depth will be taken to be 20 over 1.5. So our change in apparent depth will be 13.33 centimeter. So this will be our answer. So we're going to consider another kind of glass block. We've been considering rectangular block, so we're going to dive into triangular prism. In this case, you can have a triangular glass block. Now this triangular glass block sometimes may be said to be equiangular. Equiangular means that the angle here is 60 degree, the angle here is 60 degree, and the angle here is also 60 degree. This angle that which has been stated here in a triangular glass block is referred to as the refracting angle of the prism. And this refracting angle of the prism is usually represented with A. When we have a normal, as said earlier, we can have a normal drawn on the plane surface. So when ray of light is incident at an angle of incidence, this ray of light is refracted at an angle of refraction. Now when this ray come out on the other surface, this ray is called the emergent ray. This is called the emergent ray. Now what happened here is that between the incident ray and the emergent ray, there is an angle that is formed. This angle is called angle of deviation. The deviation now is the change in the direction of ray of light. Change from the incident ray to the direction of the emergent ray is called the deviation. So to calculate the angle of deviation using the refractive index here, most cases we always consider minimum deviation. And minimum deviation occur when the angle of incident is equal to the angle of emergent. The angle of incident here is now equal to the angle of emergent. The angle which the emergent ray makes with the normal is called angle of emergent. So minimum deviation occur when the angle of incident is equal to angle of emergent. We will now call this minimum deviation. That is D with a subscript M. In this case now we can have it that the refractive index is taken to be the sine of angle of refracting angle plus your minimum deviation all over 2 divided by sine half of your refracting angle. This is the formula we always use to find our minimum deviation. However, there is something I want you to consider here. Remember that from Snell's law, this the same refractive index is equal to sine of angle of incident over sine of angle of refraction. So correspondingly, what you have here, when we compare both sides, it simply means that what you have here is that sine your refracting angle plus minimum deviation all over 2 is equal to the sine of incident. When you take the arc sine of both sides, in this case now we simply have it that A plus minimum deviation over 2 is equal to angle of incident. Simply stating that A plus your minimum deviation is equal to twice your angle of incident. And here we have that your minimum deviation is equal to twice your angle of incident minus your refracting angle. So this is one thing I want you to always consider and put it in mind, that twice your angle of incident, the difference between the twice or angle of incident with your refracting angle is your minimum deviation. You can use this straightforward to determine the minimum deviation, as well as comparing the denominators. When we compare the denominators, we have that sine of half of angle of refracting angle equals the sine of refraction. When you take the arc sine of both sides, we have that your half of refracting angle is equal to angle of refraction. So your refracting angle is equal to twice your angle of refraction, meaning that in all cases we always have it now that your refracting angle is twice your angle of refraction. And as well, you can say that your angle of refraction is equal to your refracting angle over 2. And most cases, since the type of triangular prism we use are always an equiangular triangular prism, then we can as well have it that if it is 60, your angle of refraction will be 30 degrees. So let's take a reference question here, taken from year 2002, question 35, UTME. Calculate the refractive index of the material for the glass prism in the diagram above. This is the diagram. So from this diagram, we can denote that here this 60 degree represents our refracting angle, which is A, is said to be 60 degree. I've told you that your angle of refraction is half of your refracting angle. So angle of refraction is therefore 30 degree. From this aspect, we have that our minimum deviation is 30 degree. And I told you that there is a formula we use to determine the minimum deviation, that your minimum deviation is equal to twice your angle of incident minus your refracting angle. So if my minimum deviation is said to be 30 degree, we have that it equals twice the angle of incident minus the refracting angle, which is said to be 60. So when we bring it to the other side, we have it to be 30 plus 60, and that is equal to our twice the angle of incident. That is 90 degree, which is quite equal to twice the angle of incident. Divide by 2, divide by 2. This will cancel this. Our angle of incident is equal to 45 degree. When we use it that your refracting index equals sine of angle of incident over sine of angle of refraction, what you have as the sine of angle of incident is 45 degree, and our angle of refraction is 30 degree. So here our refractive index will be taken as that sine of angle 45 is 1 over root 2 in short, and the angle 30 will be 1 over 2. So here your refractive index equals 1 over root 2 times 2 over 1, and that is 2 over root 2. We don't usually leave root as denominator of the fraction, so therefore we multiply the numerator by the root and multiply the denominator by the root. So times root 2 times root 2, and that will give us 2 root 2 over 2. This will cancel this, we have it to be root 2. Therefore, for this particular question now, root 2 is our answer, root 2, and that is option A. But if you don't want to follow this particular method which you have followed here, we can follow a straightforward method which I have given you earlier, that your refractive index will be taken to be, that is the direct method, will be taken to be the sine of angle, will be the sine of refracting angle plus your minimum deviation all over 2, everything divided by sine of half of your refracting angle. Here we have it that your refractive index is equal to sine of, your refracting angle is stated to be 60 and your angle of minimum deviation is 30, everything over 2 divided by sine of half of A, and half of A, that is what? That is refraction. So here we have to be sine of 60 degrees. Anyways, we have to be refractive index now equals sine 45 over sine 30, and according to what we did earlier is 1 over root 2, and sine 30 is 1 over 2. So bringing back to this expression root 2, we are still getting the same answer but using different method. So whichever method which you will find pleasant to you, you can recall very much well, you use this particular method. So the last aspect we're going to consider now is we're dealing with what we refer to as the critical angle. When we are dealing with critical angle, our refractive index is usually taken to be, your refractive index is 1 over your sine of critical angle. And how do we arrive at this? It's very simple, in the sense that your critical angle usually occurs when your angle of incident is equal to critical angle when your angle of refraction is exactly at 90 degrees. So from here now we have that your angle of incident equals sine of angle of incident at critical angle. Because your angle of incident is now at critical angle, you have your angle of refraction to be 90 degrees. So and sine 90 is 1. So you have it that this occurs from glass to air and not air to glass. That is from a dense medium to a less dense medium. So in this case now, since this is occurring from a dense medium to a less dense medium, then we now have it to be glass to air. And don't forget, according to the principle of reversibility of light that I stated earlier, your glass to air will be 1 over air to glass, and that is sine C over 1, since sine 90 is 1. From here we can have it that reciprocate both sides. We have that air to glass is equal to, this one goes up and this one comes down, we have to be 1 over sine C. So whenever you are dealing with the refractive index of a material, the critical angle is, the refractive index of a material is 1 over the critical angle of that material. So now let's look at reference question on this aspect. Okay, let's consider this last reference question taken from UTME 2009 question 33. It states that if the refractive index of crown glass is 1.51, its critical angle is, that's what they're asking for. So we're looking for the critical angle. Critical angle is what we're looking for. And from the formula I've given you, we have that refractive index is 1 over sine of critical angle. So since we are looking for the critical angle, we make critical angle the subject of formula. So your sine of critical angle is equal to 1 over your refractive index. And here your refractive index is said to be 1.51. So that is sine of critical angle. When you get this value now, we have that sine of critical angle is equal to 0.6623. And here to get our critical angle, you simply find the inverse of sine of 0.6623. And here your critical angle is said to be 41.5 degrees. And that is option C. So we've come to the end of this video. If this video has been really helpful, ensure you subscribe and share with your friends. Thank you. I appreciate you guys so much for your support, and keep supporting. God bless you.